So I guess we can get started. Welcome back to the last, but certainly not least, session of this conference. This conference is on imperfect information games. My name is Michael Thielscher. I'm at the University of New South Wales in Sydney, and I've got the pleasure and honor to chair this last session. The first presentation will be given by Tetsuya Suzuki, and he will be talking about rule-based red piece inference and board evaluation in the imperfect information game called Geister.
Hello, I'm Tetsuya Suzuki from Shibara Institute of Technology, Japan. Today, I'm going to present our work titled Rule-Based Red Piece Inference and Board Evaluation in Geister. Game AI has made remarkable progress in perfect information games such as chess, Go, and shogi. However, imperfect information games remains a major challenge. In the board game Geister, players cannot see the colors of the opponent's pieces. Capturing all red pieces results in an instant loss, so the ability to infer the hidden color is essential. Our goal is to design a rule-based AI that safely infers red pieces and achieves an advantage in the number of pieces. Geister is a two-player imperfect information board game played on a 6x6 grid. Each player has 8 hidden pieces, 4 blue and 4 reds. At the beginning of the game, each player freely decides the initial placement of the pieces within their own starting area, like this. There are 70 initial configurations. The colors are invisible to the opponent until a piece is captured. Each piece can move in 4 directions: up, down, left, or right, by 1 square per turn. If the destination square contains an opponent's piece, it is captured, and the color of the captured piece is revealed. There are 3 ways to win. One is to escape one of your blue pieces through the opponent corners, like this. The second is to capture all opponent blue pieces. The third is to force your opponent to capture all red pieces. So if you capture all the opponent's red pieces, you lose immediately. This rule makes red piece inference a critical element of safe strategy. We use a draw rule in Geister AI competition. If neither player has won by the 200th move, the game is declared a draw. Previous studies include Suezoku and Oda, who propose a rule-based likelihood evaluation without machine learning, and Kawakami and Hashimoto, who propose the purple piece approach known as purple max. In purple max, during minimax search, the AI assumes the worst case for opponent's hidden colors. A captured opponent piece is treated as red, and an escaped opponent piece is treated as blue. This allows deterministic search without explicit inference. The board function used in purple max is defined like this. Here, B is a blue piece difference, and D is a difference of the total Manhattan distance to escape squares. Purple max achieved strong and stable performance, but lacked adaptive inference. The absence of active inference causes overly defensive strategies. Such AIs can dynamically adapt to the opponent's movements. Our approach, called red search, explicitly infers red pieces based on heuristic rules. This enables aggressive but safe play even under uncertainty. We propose our method. Our AI consists of 3 components: rule-based let piece inference, move selection using minimax search, and enhanced board evaluation function. The goal is to gain a piece advantage while avoiding fatal let captures. We define 8 heuristic rules, R1 to R8, to estimate the likelihood that an opponent's piece is read. These rules are designed under the assumption that the opponent behaves rationally to win. Each opponent piece is assigned a read likelihood score based on its observed behavior. For example, R1 is a rule that first piece to move adjacent to ours gains 20. R4 is a rule that an opponent piece that retreats from a position adjacent to one of ours loses 100. R5 is a rule that an opponent piece that stays on an escaped square without escaping gains 1000. R8 is a rule that an opponent that moves adjacent to one of our pieces when only one opponent's red piece remains gains 100. These scores are updated every turn, allowing the AI to dynamically estimate which piece is most likely read. Red search performs depth 6 minimax search to decide moves. If 2 or more opponent red pieces remain, all opponent pieces are treated as blue. If the remaining opponent red piece is only one, the AI triggers inference and treats the most likely red piece as dangerous. If the best move would capture that inferred red piece, it chooses the second best move instead. To avoid draws, the AI also detects repeated board states and selects alternative moves. We use board evaluation function. This is a board evaluation function. This B is the blue piece difference, and D1 is the difference of the total Manhattan distance to escape squares. This is the total piece difference, and R is a large bonus term when only one opponent's red piece remains. This formula encourages aggressive play while maintaining safety. This is experimental setup. We evaluated our method using the Geister AI competition server. The opponents were Random AI, Rush AI, and Purple Max. Random AI has 70 initial configurations and chooses legal moves uniformly at random. Rush AI has a fixed initial configuration and aggressively advances blue pieces towards escape squares. Purple Max has 70 initial configuration and uses purple pieces and minimax to decide moves. This table 2 shows the total number of matches between each AI and its opponents. For example, for Purple Max and Random AI, we use 70 initial configuration for Purple Max and 70 initial configuration for Random AI, and we change their size. So totally, we had 9,800 matches. For Purple Max, for 2 Purple Max, we used 70 initial configuration for them. So in this case, we don't change their size because they are same AI. So we use 4,900 matches. For red search and Rush AI, we used 70 initial configuration for red search and one initial configuration for Rush AI, and we changed the size. We repeated 3 times to increase samples, so we used 420 matches. We measured 4 indicators: win, draw, and loss rates. Red piece inference trigger rate. The inference is triggered when the remaining opponent rate is 1. And red piece inference accuracy. And we also measured the mean piece difference averaged over all positions within each game. This is results. This graph shows the mean piece difference per game. This is for Purple Max and this is for Red Search. Red Search achieved a mean of 2.06, while Purple Max had minus 0.26. The difference is statistically significant with, the difference is statistically significant. So this indicates that Red Search maintained a much stronger piece advantage throughout the game. However, mean piece difference and game outcome, win or not, showed no correlation. This figure B shows the correlation in Purple Max. This is for win, and this is not win. And this figure C shows the correlation in Red Search. Table 3 and Table 4 show win rate, draw rate, and loss rate of Purple Max and Red Search respectively. Win rate of Red Search against random AI and Rush AI are less than win rate of Purple Max against random AI, Rush AI. However, the win rate of Red Search against Purple Max is greater than win rate of Purple Max against Purple Max. So compared to Purple Max, Red Search performs better against strategic opponents. The inference rules work particularly well when the opponent behaves rationally. Table 5 shows red piece inference trigger rates and red piece inference accuracy. Against random AI, the inference module was triggered in 76.3 of games with 34.3% accuracy. Against Rush AI, it was triggered in 10% of the game, and accuracy is 0%. Against Purple Max, it was triggered in 99.7% of games, and its accuracy was 75.4%. In addition, Table 6 shows that Red Search won 89.7% in this 75.4% against Purple Max. Okay. So this demonstrates that our rule-based inference is effective against rational opponents, but less useful against random or simple strategies. This show, Table A and Table B show winning paths of Purple Max and Red Search. Each table shows opponent and winning path. According to Table A, Purple Max is defense-oriented it wins by self-escape. On the other hand, according to table B, let's search is attack-oriented. It wins by capturing opponent's blue. Against random AI, inference accuracy was low due to unpredictable moves. Against Rush AI, inference rarely triggered, but the AI still achieved a high win rate. Against Purple Max, inference was both frequent and accurate. So this shows that let's search adapts flexibility to various opponent types. Finally, let's search participated in the Geister AI competition 2025 and won first place among 7 teams. In the final, let's search faced EquiStrike, which used Nash equilibrium by reinforcement learning. EquiStrike won the first game, but let's search won the next 2 games and became the champion. The combination of rule-based inference and board evaluation achieved both safe and aggressive play. Let's search performed especially well against rational opponents. However, it struggled against a simple Rush AI, suggesting that further adaptation is needed. Conclusion and future work. We propose a rule-based Geister AI called Let's Search, combining heuristic inference, minimax search, and a board evaluation function. This is future work. Thank you.
All right, very good. Thank you very much for the presentation. Yep, a round of applause from everyone. Very good. We do have like 4 minutes left for questions. And as usual, you can unmute yourself, or if that doesn't work, please put your question into the chat.
I would like to ask a question. If I understood the game correctly, Geister, the number of options where which piece is which color is only 2. So there can only be red or blue ghosts. Isn't it then fruitful to use a Monte Carlo approach where you just sample, even if that's not consistent with the known information, and use this approach to infer which move is the likely best move?
Your question is that the player based on Monte Carlo will win against our minimax based.
Yes, but just for inference of the which color the ghost is, if you just sample or decide randomly, wouldn't it tend to the best option if you just sample it?
Yeah.
Maybe you don't know. Just asking for your intuition.
Yeah. This is for just reference. Participants AIs in the competition categorized into 3 types. Those based on reinforcement learning, and those employing the purple piece strategy with alphabet or minimax, and those combining n-tuple features with flat Monte Carlo search. Yeah, but in the competition in this year, the Monte Carlo based search couldn't take the first place.
Ah, okay.
Yeah.
That's interesting. Thank you.
Yeah, thank you.
I just see there's one question on the chat. Actually, it's two questions. Maybe I read the second question, or maybe I read both questions. Congratulations, first of all, for winning the competition. Well done. You said you won 2-1. Does it mean that there were only 3 matches?
Yes.
That seems very low given the randomness of the game. Wouldn't it be better to play many more matches because of the randomness?
Sorry.
Because of the randomness, wouldn't it be better to play, let's say, 100 games in order to get a much better, more robust result of who is the better program?
Yeah. In the final, we had only 3 matches. I think it is so. I can say the red search is stronger than Equus, right? Yeah. We need more matches to say which is stronger or not.
Mm-hmm. Yeah, I mean, sometimes for these competitions, this may not be a bad idea because then you can also be lucky by winning to win, and that can add a bit of fun to the whole event. But for a proper evaluation, indeed, more games would be necessary. I'm afraid we are running out of time, so let's thank Tetsuya Suzuki again for the presentation. And applause from everyone. Very good. Then we are moving straight into the next presentation, and we will hear about a Japanese game called Tagiron. The presenter is Takaaki Mizuki.
Yes. Let me share my screen. Okay. Okay. Thank you for the introduction. I'm Takaaki Mizuki from Tokyo University. This is a joint work with Koichi Koizumi. The title of my talk is Application of Secure Computation to Tagiron. So what is Tagiron? Tagiron is a logic-based deduction game. I will explain the roots later. So what is secure computation? Secure computation is a cryptographic technique which enables players to know only the value of a function without leaking any information about the inputs. So in this study, we apply secure computation to enhancing gameplay of Tagiron. Here is a table of contents. So let me begin by explaining Tagiron's rules. Tagiron, also known as Break the Code, is a popular logic-based deduction game invented by Yuhei Kurahashi. The game is played with 2 to 4 players, but we focus on 4-player version. So we assume 4 players in this talk. The game uses 20 cards called Tagiron cards. They are actually small tiles like this. Each card has a number from 0 to 9 and the color of red, blue, or green, like this. From 0 to 9, red, blue, or green. Okay. The 20 Tagiron cards are shuffled and distributed to the players so that each player receives 4 cards. The remaining 4 cards become the target to deduce. So these are target cards. Each player secretly looks at their 4 cards without others seeing them, like this. She sorts the 4 cards in ascending order, where red is smaller than blue. So in this example, red 3, blue 3, 6, and 8. They are sorted. In a similar manner, all the other players sort their cards. In addition, the game uses 19 question cards. They are shuffled and 6 of them are revealed like this. Each card has a question such as where is 9, how many blue numbers. The players take turns doing the followings. 1. A player chooses one question card and asks a question. 2. All players answer the question honestly. 3. A new question card is revealed. So, for example, this player chooses where is 9. Then all the players answer the question, say none, none, none. And this player has card 9, so he replies, it's the rightmost one. In this case, these 3 players learn that one of the targets is 9, while this player learns that one of the targets is blue 9 because he has red 9. In this way, players gain information about the target cards little by little, so they can deduce the target cards. Each player can make a challenge anytime, but only once. The player who challenges write down their guess like this. Then the player looks at the 4 face-down target cards secretly. For example, if they match, then she declares success and she wins. If they don't match, then she declares failure and she drops out of the game. So a challenge can be done only once. If player's guess is wrong, he or she is eliminated from the game. This is because looking at the target cards makes him or her gain complete knowledge about the target cards. In this study, we explored an alternative challenge mechanism. Instead of looking at the target cards, we use a secure computation, which determines whether the challenge succeeds or not. So, a player who fails a challenge only learns that their guess is incorrect, allowing him or her to continue playing. We use card-based cryptography to implement secure computation. Roughly speaking, a challenger arranges a sequence of cards such that the red card represents her guess. Then our card-based challenge protocol outputs 2 cards which determine whether it is success or failure. So by using card-based cryptography, we propose a method for securely determining whether a challenge succeeds or not, without leaking any information. This provides new game variations of Tagiron. For example, a version could allow players up to 2 challenges. Okay, so I guess card-based cryptography may be unfamiliar, so let me explain it. We use 2 types of cards, black cards and red cards. The order of black to red represents 0, and the order of red to black represents 1. If a bit X is encoded with 2 face-down cards, then we call them a commitment to X. Now let us consider a card-based AND protocol. So given 2 commitments to X1 and X2, we want to obtain a commitment to the AND value X1 and X2 without leaking any information. Okay, so we place x1, x2, and 0 here. Please remember, please note that x1, the product of x1 and x2 is equal to 0 if x1 is 0. Otherwise, it is x2. Okay, so if x1 is black to red, then this becomes x1 and x2. If x1 is red to black, then this becomes x1 and x2. Okay, so x1 and x2 is always below the black card. So we shuffle the two portions randomly. Then we open the top cards. So there are two cases, but in either case, the two cards below the black card are a commitment to x1 and x2. So we can obtain a commitment to x1 and x2 without leaking any information about the inputs. So this is a typical card-based AND protocol. Okay, so let me move on to the pre-processing protocol. It processes information about target cards before the main protocol is executed. In addition to Tagiron cards, we use number cards from 0 to 19. So we use the following correspondence between Tagiron cards and number cards from 0 to 19, like this. Tagiron cards along with number cards are distributed together. Okay. Tagiron cards are used as in a normal game, while number cards are used in the processing protocol and challenging protocol. These are number cards. We place 0 above player's cards. That is, we place black to red from here to here. We also place 1 above the target cards. That is, we place red to black here, from here to here. Okay, so only target cards are associated with value 1. Other cards are associated with 0. Okay. So turn over all face-up cards, and we make 3 card piles like this. Okay. And then we apply a shuffle to the 20 piles like this. Then we open the bottom card of each pile and sort the piles based on the bottom cards, 0 to 19. So we now have these 3 sequences such that a card is target if and only if the corresponding commitment is equal to 1. So for example, if the target cards are like these, then here and here and here and here have value 1. Okay. So this is the processing protocol. Okay, let me move on to the challenge protocol. By the pre-processing protocol, we have 3 sequences, as I mentioned. Okay, so a card is a target card if and only if the corresponding commitment is equal to 1. Let us consider a situation where a player wants to make a challenge like this. So her guess is 1, 3, 6, 9. So in this case, her guess is here, here, and here, and here, and here. Okay, so let's denote these values of commitments by C1, C2, C3, and C4. Then her guess is correct if and only if C1, all of C1, C2, C3, and C4 are equal to 1. Okay, so the product of C1, C2, C3, and C4 is equal to 1, then it implies success. If C1 and C2 and C3 is equal to C3 and C4 is equal to 0, then it implies failure. So the problem is how to secretly select the 4 commitments corresponding to the case. Let me explain how to doing so. How to do so. So first, a challenger arrange a sequence of cards like this, such that red cards indicate her guess. So she put a red card here, here, and here, and here. Okay. According to her guess, she plays red cards. In other positions, they put black cards. Then she turns them over face down like this. Next, we turn over all the cards and make a pile and shuffle, apply a shuffle. Then we open the bottom cards. So 4 red cards must appear. The cards above each red card correspond to her guess, right? So we take these commitments, C1, C2, C3, and C4. We apply the AND protocol as which was introduced in section 2. Then we obtain a commitment to the product of C1, C2, C3, and C4. Finally, we open the commitment. If it has the value 1, then it implies success. If it is black to red, I mean it is 0, then it implies failure. So we can only know whether the challenge succeeds or not. This is our challenge protocol. So let me conclude my talk. In this study, we apply card-based cryptography to enhancing the gameplay of Tagiron. We believe that it is useful to promote intuitive understanding of secure computations to non-specialists. The number of cards used in our method is not so small, so I admit that it is not so practical. So further optimization is future work. That's all. Thank you for your attention.
Okay, very good. Thank you very much.
You're welcome.
Round of applause from everyone. That was slightly, but just 1 minute longer than the 15 minutes, so we still have a couple of minutes for questions. And again, either please unmute yourself or use the Q&A chat to type your question. Anyone? Maybe someone's typing, and while someone's typing, I might ask a couple of questions that I had. You did mention that with your approach, it's quite easy to consider variations of the standard rules of Tagiron. And I think you mentioned, for example, you can deal with a variation where a player can have more than one challenge.
Yes.
2 challenges is what you said. I'd be curious to hear what other variations you think would be very easy to obtain in your setting.
Okay. Okay. I think considering Tagiron this game, I think
Like, can you introduce
Yeah,
new
I mean,
question cards, for example?
we focus on the challenging mechanism. So, yeah, I mean, we can. It is not so easy to expand our result to other to expand other rules. So yeah, it would be a good future direction.
So something like adding additional questions, for instance, I imagine that would not be difficult.
Adding other questions. Actually, the question is coming from the question card, or so.
Yes, and could you think that you could easily extend this to other questions like prime numbers?
It's possible, but it isn't so related to our method. This work actually, we just propose a challenging mechanism. So question cards are used for collecting information. So,
but then for the challenging, it wouldn't make a difference.
Yeah. Sorry.
Can you see any other applications of your work beyond this game? Any other games where this would be of interest?
That's a good question. Cloud-based cryptography can be applied to other games. Actually, there are several existing works, such as Uno, or a card game Old Maid. So, using cloud-based cryptography, we can create a virtual player in Uno or Old Maid. So, actually, this is a hot topic in this field.
Is that something that you will look at next? Is that on your to-do list for future research?
Not really, but I hope you could give me some examples if you know good games.
I would have to think about it. Maybe someone else in the audience here has other ideas as well. But I think I don't see any other question on the chat.
I will have an additional short question. And the short question is, have you played this with humans and have you noted down the results? And what was the best human you saw?
Sorry?
In fact, my question comes down, what was the best performance you saw when you selected participants to play this game?
What is the best solution?
Now, not the best solution. The best solution is, of course, that they immediately give the correct answer. But nobody gives correct answers, as you may understand. So they make steps, and steps. Yes?
So there are 19 question cards. So until 19 cards are, I mean, normally using 19 cards would lead to the correct guess, actually.
I think that your answer is that everybody finally solves the game for his position, for the position you give him.
Sorry, I couldn't quite get that. Sorry.
Yeah, maybe this is possibly better to formulate by email and by text between the two of you. I think the Takaaki didn't quite understand the nature of your question, so maybe by email would be better because we are running out of time. Okay, thanks again, Takaaki, for the presentation and this work. And we will get on to the very last, but certainly not least, presentation of the session and the conference. And this is given by Lukas, and he will be talking about information set computation in imperfect information games and using answer set programming for this purpose based on the game description language.
Thank you for the introduction. My name is Lukas Grassauer. I'm representing Austria, TU Wien to be exact, and I'm presenting my paper on leveraging answer set programming for information set computation in imperfect information games. imagine you're building an autonomous agent to play the game Battleships. Your agent can only see where it has placed its ships, but not the opponent's. And at each decision point, it has to reason where the opponent's ships could be. For example, answering the question, where is the aircraft carrier? And while this problem seems simple enough, when the game progresses and more cells are revealed, generating histories or possible states that are consistent with the observed information gets increasingly difficult. Even more so in the context of general game playing. Current methods force us into an uncomfortable trade-off. Depth-first search-based methods usually lack performance without optimizations. Other methods that are more sophisticated sacrifice completeness, meaning they could miss important valid states or permit invalid states. And other methods use game-specific optimizations, defeating the purpose of general game playing. So I've asked myself if there isn't a way to leverage answer set programming, which is a paradigm often used for logical inference and constraint satisfaction, for this method, for this problem. And based on the work of our session chair on answer set programming for single player games, and the work of Richards and Amir on using constraint satisfaction modeling on information set generation, I've investigated during my PhD thesis whether answer set programming is a viable option. And yes, it turns out that answer set programming makes information set computation tractable even for complex imperfect information games while maintaining completeness and generality. What makes answer set programming such a good fit? And does it actually deliver in practice? Well, let's look at how game description language, or GDL, is translated to answer set programming programs, and how integrity constraints, a native concept in ASP, can be used to express known information. And then let's look at how ASP fares against DFS in a direct comparison across two games. So how does answer set programming deal with this problem? Let's first look at a simple example using a very simple tree with two players, which are denoted as triangle and circle. And an outside observer sees that the current history is F1, S2, and FA, leading to the current state U. However, the player triangle cannot distinguish between A or B, and they don't also have the information that S1 or S2 was played. They don't know which one. So either S or U are both possible states. And this is what we call the information set. And incorporating this information into the game tree is where ASP excels at. So how does the method actually work? Let's look at it on an example basis. So GDL, game descriptions, which is a logic based paradigm, are translated by step into ASP rules. The first major module is called state transition, where the rules regarding the state machine are translated into the temporal variants. And important here is that some rules receive the same name. So next, for example, is translated into holds at, and true is also translated into holds at. You can see this in the center column. This rule is regarding battleship, whether or not a cell was hit after a shot. And the temporal variant is structurally the same. However, the head of the rule is at t+1, and the body of the rule assumes t. And this t spans between offset and horizon, and these can be freely chosen depending on the needs of the agent. Well, this state transition module spans a search tree and spans a search space rather. And the next module, enumerating possible states, routes this search space. And the simplest variant is to use the initial state using the init rules, and then translating it into holds at point 0. And this routes the search space, and the next module describes how this search space can be explored. And namely, this is done using holds at with control, so which roles are in control. And for each role that is in control, there is a set of legal options. And using a choice rule, one of those options is chosen for each possible state, and explicitly excluding terminal states. So these three modules, together with the next module, form the method. And the next module is called asserting known information. And this is also illustrated best using an example. So again, using battleships, the player left has made 5 moves, going, some are hits, some are misses, and these are denoted on the top right-hand side, where only the moves are denoted. And on the bottom right-hand side, the observations left has made are shown. And using only those few integrity constraints, all histories which are inconsistent with the observed information are automatically filtered out. And once such information set is computed, it can be used to start subsequent searches. Let me explain what I mean by that. If you look at our tree example again, where S or U are the possible states, there we can use holds at rules again to describe the states using, for example, S and U, and deleting the old enumeration of the possible initial states. And then use a choice rule to make them mutually exclusive. And this saves a lot of time on effort if the game is a long ongoing game, because we don't have to start the search at I again or in the initial state again. So hopefully I've convinced you that this problem, it can be elegantly solved using ASP. And now let's look at the performance. How does it actually fare in practice? And to do that, I've used 2 games and used DFS as the baseline. Let's look at the methodology. So the 2 games chosen were Phantom Connect, sometimes also called Blind Tic-Tac-Toe, in its variant 4-4-4, and a little bit harder variant 5-6-4, and Battleships, the running example from before, which used 6x6 grid with 3 ships, also called mini battleships, and the full-size battleship 10 in a 10x10 grid with 5 ships. And for both of these games and each of its variant, I've generated 100 histories in lengths 1 to 10. So starting from the initial state, leading to an arbitrary descendant state at that length, and stripping out hidden information for one player. And the methods had then were tasked with generating consistent histories with the leftover information. And this was limited in a 60-second time limit. The methods used were ASP, using Klingo as a solver, DFS using SWI Prolog as GDL reasoner, and to compare Klingo as a GDL reasoner and the method itself, I've reused Klingo as a GDL reasoner. So let's go to the results. The x-axis shows the length of history, which is also increases the complexity. And the y-axis shows the average number of histories generated per second. And note that this axis is scaled using a log base 10. And the results show that for Phantom Connect, ASP beats DFS in almost all instances and is also comparatively stable even for long histories. And for DFS, this is not true, so it's steadily declining, even for long ongoing games, or especially for long ongoing games. For battleships, the gap is even more exaggerated. So ASP is able to generate tens of thousands of histories per second, even for games of length 10, while DFS is relatively poor at tens or a few hundreds of histories per second, or even timing out before generating one history. The second metric we've looked at was completion rate. And completion rate means if the search space was exhausted. So in this metric, ASP also excels. And for the easier games, it even exhausted the search space for all possible histories. And for the more difficult games on the right-hand side, it exceeds DFS. So to quickly review, we have looked at how GDL is translated into ASP and how we can use integrity constraints to express known information, and that is used to filter histories and with that information sets. And then we've looked at what the empirical evaluation says about ASP and DFS in comparison, and ASP significantly outperforms DFS. In conclusion, computing information sets with ASP is tractable, even for complex imperfect information games. And future work, which I will tackle during my PhD thesis, will include more benchmarks with more comparative methods other than DFS in especially game-playing contexts. Some theoretical analysis into the runtime and grounding size and investigations into formal validity. Some left on the table optimizations, and beyond information sets also have previously seen there is a paper by our session chair or co-authored by our session chair solving two-player games using a similar method called quantified Boolean formulas, but also probably using ASP or maybe using ASP to solve two-player games as well. And finally, I would like to share with you the code used to run the experiments and the game descriptions of the games, which you can use the QR code to get there or the link below. Thank you very much for your time and attention, and I'm very much looking forward to your questions.
Okay, very good. Thank you very much. Another round of applause from everyone. That was very well in time. We do have a few minutes for questions. Just a quick comment to what you said at the very end. Indeed, the QBF uses QASP, quantified answer set programming.
Mm-hmm.
But then
very interesting topic.
I couldn't agree more. Questions? Either unmute yourself or type into the chat. And while everyone may be thinking about questions, one that I had was, why did you limit it to the length 10? It would have been interesting to see what happens if you go longer and longer. Of course, for very short games like blind tic-tac-toe on a 3x3 board, it doesn't make sense to go longer. But for many of the other games, I think the maximum depth would be much longer than 10.
Yes, I agree. This was the arguably limitation in the experiment design. I think the rationale was to show that it is quite more performant than DFS. Regarding longer games, I think it would also be interesting to show the contrast by starting from the initial state and going from one particular state where the information set was already computed. So also contrasting the performance differences in the method itself, depending on how you apply it. Unfortunately, for the paper, it was rather space intensive to do more experiments. So I've chosen to arbitrarily limit it at depth 10.
But I mean, from the graphs that you showed, there was not a significant decrease in the performance. So I would assume, and this is why I would be interested to see this, that it would still go well beyond the 10 with pretty good performance.
Yeah, I agree. This is, of course, something which will be interesting to look at in future work, especially in game playing contexts, because generating histories and generating information sets is one thing, but playing strength is another thing. So is this method also comparable in playing strength? Because this is what the next graph shows. It's very difficult to exhaust the search space even at that length. Perhaps it's better not to exhaust the search space, but rather have a very diverse set of samples, if that's not possible. And there is also interesting work on, I can show my QA slides on that by Romero, Schaub, and Vanko about computing diverse, optimal stable models, which tackles this problem because sometimes answer sets are very similar to each other, or the Hamming distance is very similar to each other, making stream sampling rather difficult. And this would be a very interesting add-on to this method as well, especially for long ongoing games.
Thank you. Any other urgent question?
No, not an urgent question, but what is your own next step in this case? That was the question also, because this is what you could master and also what you communicated to us quite eloquently. So thank you for the presentation. But any presentation which finishes well calls also for a new challenge. And so my question is, what is your new challenge as a sequel to your own research?
Thank you very much for the question. So I can tease that or hint at that. I'm currently investigating if we can use answer set programming to solve two-player games, because this is not trivial, because it's very difficult to express multi-optimization or adversarial optimization problems using answer set programming, but using modern solvers, which can leverage incremental grounding and propagators. I believe it's possible to use these methods to also solve two-player games. And this is maybe sounds different to the problem I've tackled here, but it's all based on the work of Michael Thielscher on using answer set programming on single player games. So it's this is the road ahead, so to say.
Okay, I wish you much success with the I would say the sequel of your research, and also the termination, of course, of your PhD thesis.
Yeah.
Very good. Lukas, yeah, I can recommend to look into the quantified answer set programming approach that we took, but we didn't look at imperfect information games, so that would be interesting to see as well, even if you have just one player against nature or then two players against nature. So that's all interesting questions.
If you're open to that, I would be happy to send you or contact you and ask you many questions about this, if you're open to that.
Yeah, please do that. I'm happy to do that, of course. Yes. Okay, so we are well over time. Thank you again, and thank all the speakers of this session again. And I then apologize to the program chairs that it's a few minutes later than should have been, but the program chairs, they do want to have the final word for this conference.
Sure, thank you, and no worries there. I think it's better to have nice discussions than to be perfectly on time. So that's perfectly fine. So thanks a lot, Michael, for taking the time to chair this session, and thanks to all the speakers of this final session.